Hey everybody, welcome back to AIT 1203. My name is Mike Deal. I'm your instructor. So far we've talked about hand tools, we've talked about fasteners and proper torquing and proper application. Well, now we're going to talk about drilling and tapping. Sometimes you sometimes weld materials together, metal materials together, but sometimes that's not always an option. So drilling and tapping is your next best bet. So we're going to talk about how to do that today, how to properly drill and tap holes, properly size it for the hardware, and make sure that you're going to be able to get that final torque on it. Okay, you get a hole too big, you can't get the torque on it. You get a hole too small, and then you get an improper torque value for your fastener. Remember, we're trying to stretch those bolts when we're putting fasteners in. The idea is to stretch it, give it tensile strength, okay, so it can do its job in holding material together. So let's go ahead and move forward. First thing we're going to talk about is the drills, the taps, and the dies. Okay, a couple of images of all of these, some dies and some taps. Okay, so the first thing we're going to talk about is drills. Now, you've seen drill bits probably most all of your life, but a little bit about what you need to know about them is that drills are numerically or alphabetically or fractionally sized. Okay, and by that, each one of those values, whether it's an alpha character, where there's a numerical character, where it's a fractional, they're going to step it up or step it down in size. Okay, the proper bit must be used to ensure that you have good thread material engagement with our fastener and the material. Okay, so it's critical that we follow whatever size it is we need to use based on the size of the hole. Now, where do we get that information? Well, there are a lot of drill and tap charts out there available. I've got some in the lab. Actually, one of our vendors supplied us with some drill and tap charts. Critical information as to what size of hole and what type of tap you use for a particular piece of hardware or the fastener. Okay, I don't expect you to read this off the screen. It's kind of small, but you'll see something very similar to this in the lab by the drill press. Okay, so for example, if we wanted to drill a 1/4-28 hole, now remember we've already talked about fasteners, but let's review real quickly. A quarter means it's nominal diameter. Okay, the diameter of the hole of the fastener, and then the -28 is the number of threads per inch. Okay, so we'll have a 1/4 inch diameter, and we should count 28 of those little thread peaks that we talked about. Should count 28 of those in a 1-inch span. So just a real quick review there. So we want to have a hole that will facilitate a 1/4-28 fastener. Well, in order to do that, we'll just go to our drill size, and we need to use a number 3 drill bit. Okay, again, that's a number 3. That's a numerical bit. Another example, if we wanted to do a 5/16 18 hole, okay, 5/16 inch diameter, 18 threads per inch. Okay, we're using size F. Okay, it's specifically sized for that. All right, that's the size that works best. And again, we have fractionals, as we said earlier. For the 1/2 inch 13, we're going to use a 27/64. Now, it gives you the decimal equivalent. It tells you whether you're coarse or fine, a little extra information on there. But these charts are invaluable, particularly when you are going to drill a hole. You know what you need. Usually they're placed somewhere around the drill press, conveniently located for you to be able to find that information. But a 1/4 inch hole, you do not drill a 1/4 inch hole for a 1/4 inch fastener. Okay, it would be too wide. It's a through hole. We're going to talk about that in just a little bit too. But let's talk about the anatomy of a drill bit. Okay, I don't want to get into real heavy detail on this, but I just kind of want you to know what a drill bit's made up of and the different parts and the terminology as well. Okay, the entire length of this drill bit from here to here, the entire length up to here, is known as our shank. Now, where the flutes start, these are the flutes, that's sort of the spirals. Okay, the spirals in here are known, this area from here, that full length there, is known as the body. And again, these little channels that are helically cut into this drill bit are known as the flutes. Now, the flutes allow the chips, once they start to come out of the material, we drill it out. These flutes allow the material a place to exit. Otherwise, they just stay packed up in that hole. So we want to pull those chips and those spirals out of our material, and that's part of the transportation or transport area of the drill. It allows the material to come out for us. Okay. We've got the drill tip. That's the very end. That's where the body ends and the very tip of it ends right there. So that small area right here. This is the part that does the cutting for you, okay? None of this does any cutting. This is, again, to transport spent material away from whatever it is we're drilling. But you've got this tip, okay? And the diameter itself right here is the size of the drill itself. Again, I don't want to get a whole lot into detail, but you can see the point angle here, the angle at which it is cut. There are various degrees. There's some 8-degree angle bits and some other, you'll have various angles depending on the material that, that you're going to be drilling, okay? Over here you've got your chisel point. That's the very, very tip part right there, okay? That's our chisel point. That's the part that starts the actual digging and boring process, okay? Once it's kind of clears its path, then the lips can come in here and start to tear out the material. The material then travels through the fluted area and then exits the drill. Okay, just a little bit about the anatomy. The shank, again, is the part that you're going to chuck up in a drill. Some of you have never actually even chucked one up, so we're going to be doing that in the lab. I'm kind of excited about the lab for this one. But anyway, the project you're going to be making, it's going to be pretty interesting. There's going to be something you can take away from it too. But this is sort of just the anatomy of a drill bit. And so you will want to know these terms, pertaining to the drill bit. So be sure that you're taking notes with this lecture as well. We'll get into it in the reading as well. Okay? So we don't just chuck up a drill and just go to town on drilling a hole, okay? It really depends on the type of material that we're drilling. We could be drilling cast iron, we could be drilling soft aluminum, brass, mild steel, hardened steel, all these different types of materials, and they have all different speeds at which the rotation of the bit will rotate, okay? If you run one too fast, you're going to burn it up and dull the cutting surface of the drill. If you run one too slow, okay, it's not going to be very effective, and it will also burn one up too. So really, the speed depends on the material, okay? The softer aluminum, like I said, the aluminum, the brass, and things like that, that's for a higher RPM. You can cut it a little bit faster, okay? The harder materials, your mild steel, your cast iron, your stainless, you need to go much slower. And faster, slower, how do we know what speed to go? Well, it really depends on the material, and there's a formula that we use in order to determine the speed. Just a side story, I had an uncle of mine who was trying to install a roll bar, or roll cage, I should say, into a frame of his Jeep. And he was using this mild steel bit, real high RPM in a hand drill, real high power, just going through them left and right. And he asked me, he said, I don't understand, maybe it's the type of bit I'm using or what it is. And as what it turned out is he was trying to drill that hardened steel of that Jeep frame way too fast. It was, I mean, he didn't get more than 10 seconds. He was burning up bits just like that. So what we did, we slowed the RPM down. We used proper cutting oil, and it just started pulling spirals out. Next thing you know, he's got success drilling that hole. But that's just a little experience I had there using the wrong speed. I would never use the wrong speed. I'm just kidding. I've done it before. Anyway, determining the speed. Let's talk about this for a second. Each material has a surface foot or surface feet per minute value. Okay. You take that surface feet per minute value and then you multiply it by 4. This 4 is a fixed number, it's a given number, and then you divide it by your drill diameter, and that will give you the RPM at which you should probably be drilling the material, okay? Or somewhere close, okay? Let's take a look at, for example, if we've got a 3/8 inch hole, all right? Now I'm going to be drilling it in aluminum, and aluminum is 200 to 300 surface feet per minute, okay? Now, we've got our drill diameter of 0.375, okay? If you want to know the decimal, how to find that, just divide your 3 by your 8 and come up with a 0.375. That's the drill diameter. So, we know our surface feet per minute. I use 200. I got a range between 2 and 300. So I'm going to use 200, multiply it by 4, and get 800. We're going to divide that by 0.375, which is our drill diameter, and then we should be drilling a hole at about 2133 RPM. It does not have to be exact. If you were between 2100, 2200, even 2000 to 2200, that's going to be close enough, okay? But that will give you a targeted RPM to go for, and then you can kind of adjust it a little bit here and there, okay? When you go to our drill press in the lab, you're going to see an RPM dial indicator up there on top that you'll be able to adjust and pull dial your speed in to what you want it to be. But this is the formula that you're going to use to determine the speed of the drill. Okay? Now the feed rate, when you're using a drill press, is a little different. Some of you may have had some machining classes where the feed rate's a very prescribed value, and the machine will feed the bit into the material. That's what we're talking about, feed rate. How fast that bit is going into the material. All right? So when you've got a lathe, that feed rate can be adjusted by the machine and it will automatically do it for you. When you're pulling on the handle of a drill press, it can give you a lot of variability, okay? It's not as precise. So how do we kind of adjust, or how do we determine that feed rate? All right, well, a couple of things. It is difficult to regulate with a drill press. First of all, we do have to have some cutting oil, okay? We want cutting oil, unless we're cutting like a cast iron or something like that, like on aluminum and some mild steel, things like that, we will want to use a cutting oil, okay? And we want to cut just enough, we want to pull that feed rate in just fast enough to get a good chip curl, okay? It's kind of like a spiral or a pigtail sometimes it's called. We don't want to go too fast, okay? Because that will break the bit. There's a possibility of breaking the bit, okay? And also it will mar the inside of your hole. You wind up with a really sloppy hole or one with some cuts in it. So you want to make sure not to go too fast. If you're smoking a bit, that's not a good thing, okay? We want to avoid that at all costs. Oil will help with that, but feed rate will primarily be the determining factor of whether you get smoke or not. Again, smoke, we don't want that. It's not a good thing, okay? So when I'm talking about cutting oil, all right, there's a couple of different kinds we can use. 3-in-1 is a good cutting oil. WD-40 can be used for some of the softer materials. Okay, these are good for softer materials like aluminum, okay? For brass, it's even suggested that you use kerosene. I personally have never used kerosene. I would stick to something like, WD-40. That'll be just fine for soft material. Like so on cast iron, you don't use any oil at all. We're going to be cutting at a very slow RPM. We want it to cut, okay? And that lubricant will sometimes be like a barrier or a riding surface between the bit and the material. We don't want that. What we want is we do want that to cut, but we're going to cut a cast iron or something very hard at a very slow RPM. A lot like that Jeep frame that I was telling you just a few minutes ago is a very hard hardened steel, so you have to cut it nice and slow, okay? And sometimes just using air to pull the material out of the way is good enough, okay? So let's talk about taps for just a second, okay? Taps are these things here. Okay, here's one I've got for you as an example. I can kind of bring it up to the camera a little bit. All right, tap is going to give us internal threads on whatever material we're cutting. Okay, several different types of taps. It depends on what type of hole that you're tapping as to what type of tap you're going to use. Okay, so again, it's used to cut internal threads. In other words, the hole right here is going to have internal threads to the hole. Okay. The helical design is designed to pull the tap into the hole, okay, and then it cuts material out and it leaves the desired hole and the thread pitch that we're looking for that particular fastener, okay. All right, so we've got a couple different types. This is just a little different image there as it's going into the material from this cutaway here, all right. So when we're tapping smaller holes, this is a little bit exaggerated, a little bigger than we need. There's a tap handle available. I don't have one with me right now, but there's a handle very similar to this, like a T handle. And you put your tap in here much like it's shown here in the image, okay? So when we're tapping smaller holes, we can use this small tap handle. It's got a little T in there to give us a little leverage to pull on. This nut will tighten up and sort of chuck up the tap in the tap handle, okay? And we'll usually cut with a little cutting oil. And we'll start working our tap into that blind hole, all right? And we'll start creating threads as we dig deeper, okay? Again, the tap has it's a hardened steel, it's a very hard material, and it's got these very sharp teeth in here that cut the material away, all right? And then you'll notice it's got some flutes. Now, they're not helical, but they're sort of, they're flutes to hold material. Once it cuts it, the chips that it's cutting away and the material it's cutting away will land in here in these flutes, and you can back it out and clean it out and go back for some more. Okay, it's a progressive procedure. But usually use some cutting oil, and the cutting oil also, not only will it help facilitate the tap going into the material and make it nice, working with the tool and everything, it'll also help the chip collect in those flutes that I was showing you. It'll kind of keep it collected there and bound together. Okay, but we want to make sure to use the tap handle, and we also want to make sure we use some cutting oil. All right. This is sort of the procedure that we go through. We'll drill the first hole into our material. Okay, and this is what we call a blind hole. This is the material right here with the diagonal lines. Okay, we'll drill all the way through. Okay, and then remember, this is not like if this was a 1/4 inch hole we were trying to fastener that we were going to use as a 1/4 inch diameter. We're not going to drill it a 1/4 inch. We're going to refer to our tap chart, use the proper drill. So this will be the tap drill diameter, not the fastener diameter. So we're going to drill that to the certain length that we want right there, okay? And then we're going to cut our threads with our tap, okay? Okay, our tap will go in like this. It's a little exaggerated here, but we'll go in like this, and we start cutting. Now, when we start cutting our threads, you'll learn this in the lab. Typically, you don't want to just start running it down like a fastener, okay? We're cutting material out, and that material's got to go somewhere. It's got to get out of that hole so we can continue to go down further. It's sort of like digging a hole without pulling the dirt out of the hole. You just keep digging and digging. It's a lot better when you pull the dirt out of the hole. The same thing applies here with the tap. We go perhaps maybe a 1/2 to 3/4, maybe even a full turn, and we want to let it, you'll notice it's very difficult to try to start cutting that material out, or more difficult, I should say. Back it out and let some chips come out, go back for another 1/2 turn to a full turn bite, and then back it out. And it takes a little while, but the idea is that you want a nice clean hole. If you get some chips that are jammed up in there, they can mar the threads, and you don't have a good clean hole for your fastener. So we have drilled the hole, we have tapped it, and then of course our fastener will fit right in there, and our teeth will engage with the fastener teeth there on the fastener threads will engage with material threads. So we've cut an internal threads to match the external threads of our fastener. So that's just a simple step of the procedure that we go through to tap a hole. Okay. Another critical thing you got to do is when you are holding your tap. Okay. Again, you're going to have a tap handle. But you've got to make sure it's perpendicular to the material, okay? If you get it a little bit to the left, a little frontwards, backwards, whatever, if you're not perpendicular all the way around, okay, you're going to wind up with a crooked hole, and then you're going to wind up with a bolt trying to go in like this, okay? Not going to work. So we want to be very careful. This image right here shows using a square to make sure that we're good and square. You want to check it every 90 degrees from one another. So if I check it at the 12 o'clock, let's use this one. If I check it at the 9 o'clock position, okay, that means it's perpendicular to that axis, and we're going to turn it 90 degrees and double check it to make sure it's not leaning the other way, okay? So you just need to check it at 90 degrees from each other to make sure that that tap is nice and straight, okay? Again, a misaligned tap means you're going to have a misaligned hole, okay? Now, there's a couple ways to do this. Again, we talked about the tap handle, okay? There's another way that you can do this, and you can put your tap in a drill press, okay, chuck it up in the drill, and then slowly turn the chuck. Now you are not, I'll make sure if you don't get anything else out of this lecture, make sure you hear this. You're not going to turn this drill press on and run this thing down and make a hole very, very fast. You should really, if you're going to do this, it needs to be unplugged. Okay, that's part of your lab procedure, is to make sure that the power is disconnected from the drill. And they're using a small dowel pin in the hole of the chuck, and they're twisting it a little bit to get some grip to it, and it's slowly feeding in there, okay? That's one way to do it. There's a tap handle this way. Another way to do it is to use a live center. Now, I've got a live center right here. And a live center chucks up in the drill just like a bit would, okay? We would chuck this part up right here, and this is what you've got as a live center. And what's going on here is this allows us, on some of our taps, for instance, this one right here, I don't know if you can see this or not, but there's a hole right here in the end of this tap. And that hole is there to accommodate the tip of this live center. Okay, and here's the live center. And you'll notice I'm holding this still, and I can spin it like this, okay? That center will spin for us. And what we want to do is we want to chuck this thing up, and this will let it spin, okay? This will let it spin, and we can apply pressure with our drill press handle, put some downward pressure. In this case, they're using a wrench on the square of the tap, and they're applying a little pressure as they turn the tap. They're going to turn it for about a half turn. They're going to swing this wrench for about a half turn, maybe a full turn, depending on the material, and they're going to back it off. And you can apply pressure until it starts to take hold and bite itself, and then it'll start pulling itself in there. But to get it started, one method to do that is to use a live center, okay? You'll see a lot of live centers in machines, like on lathes and things like that. But you can chuck these up and drill and use this configuration, and it makes for a beautifully aligned hole, okay? When you're using this method, you don't have to worry about a square, whether it's perpendicular, because it should be perpendicular as long as the table on the drill press is perpendicular, okay? So that's another way to ensure that when we tap a hole, that it's getting to be that it is perpendicular, okay? All right, again, you can also use a tap wrench, okay? Same procedure. Instead of a wrench, you can use a tap wrench, slide it over the end of that tap, chuck it up. A little bit more difficult to do than the live center, because you're going to have to go over the tap, then chuck it up. So it's a little bit more cumbersome, but we've got a live tap for you to use in the lab, so I just thought I'd throw that up there, okay? Now, there are 3 types of taps, and yes, it makes a huge difference as to which one you use, okay? First one we're going to talk about is almost the beginning tap, the first tap. It's a tapered tap, okay? And again, you're going to need to know all this, so I'm hoping you're taking notes while we're talking. The tapered tap is the beginning, is the first tap you're going to use in a blind hole, okay? It's got a long, gradual taper right here, okay? Now, this makes it start really easy, okay? Because you have a taper going into that hole, and it lets it feed itself in there a little bit easier, okay? So it's going to be an easy start, and it's easier to keep square with the material, okay? But you'll notice that the taper starts here, and it goes almost half the distance of the cutting teeth here. So you've got a nice long taper. You can get it in there straight, work it around, make it sure straight, unless you have the live center and the drill press that we were talking about. So you'd still want to use this, okay? This is our starting tap, okay? Now, the next one is a plug tap. Once we have run this as far into our hole as we can, now, this may go all the way through the material. It may be a through hole, or it may be a blind hole, meaning that it stops sort of like right here. It stops dead in the material. Or it could be a through hole that goes all the way through. But regardless, when you start that taper tap, the next one we want to follow up with is the plug tap, okay? It's got less of a taper, so it starts cutting sooner and cleaning out, but you'll notice that it goes deeper into the hole. These are your final cutting teeth right here in this area right here. And you'll notice that you've got this much distance from the cutting teeth to the end of the hole, as opposed to this one where you've got this much. So you're basically going in a blind hole, for example, you're going to have this much of your hole without teeth that will engage, or threads that will engage our fastener. So we can pull this one out, we use the plug tap, and then we get more threads for engagement deeper into the hole, okay? So that's our plug tap, okay? And again, it cuts areas where the taper tap can't get to. All right, and then finally we have the bottoming tap. Now, the bottoming tap, again, is going to be for holes, blind holes that don't go all the way through, okay? If they go all the way through, you can finish out with a plugging tap and run it all the way through up to here, okay, in the tap. But if you got a blind hole, you'll need to use a bottoming tap. Now, this example I've got here is blind. It's a bottoming tap, okay? But you'll notice right here, there's very little taper. I mean, just a couple of threads. I mean, a couple of teeth right there that are going to be used to cut. All right. So it's got almost no taper at all. It makes threads that are going to be engaging in the fastener deeper. Okay. So now we're going to look at just a small amount of that hole. It's going to have no real threads cut into it. So we have gone from this much area that's not going to have threads to work it down to our bottoming tap to about that much, and kind of giving you a visual as to how much material you're cutting out. So the bottoming tap is used to cut as close to the bottom of the line hole as you possibly can. There's no real reason to use a bottoming tap with a through hole, because again, the plug tap, the plug tap will go all the way through, so you're going to be cutting your final teeth there. The bottoming tap is used primarily for blind holes, okay? All right, and again, there's a couple of examples here. You've got your tapering tap, and we start with 7 to 10 teeth in our taper. Okay, that's about 7 to 10 teeth that are not going to cut the material to where our fastener will engage. Okay, but that's our starter. We come back here, and we've got 3 to 5 teeth of taper in our chamfer here, our taper. Okay, so we're going to be cutting more teeth a little bit further into that hole, and then again 1 to 2 teeth in our bottoming tap. Okay, important information. I want to write this down. Okay, you might see this a little bit later. So again, there's 3 types of taps: taper, plug, and bottoming, and here are their characteristics. So if you need to stop the video here, take a look at it, and get your head around it. That's a good idea. Okay. The information on the taps themselves is usually inscribed on the shank of it. Okay, right below the square where you put your wrench in before the threads. It will give me, for example, this is a 3/4 tin. This is designed to cut a hole that will accommodate a 3/4 tin fastener. Again, 3/4 tin means it's a 3/4 inch diameter fastener with 10 threads per inch. Okay, keep going over this over again and again. So it gives us our nominal size and our threads per inch. This one's a 3/8 20. Okay, you should know what that means. All right, this is the type of material that the tap is made out of. This is a high-speed steel. Okay, HSS is a high-speed steel. The pitch diameter limit is a GH3. I'm not too concerned about that. And the thread form is, I'm not too worried about that either. The biggest things you're going to be concerned with is the nominal size and the thread per inch. That's going to be the critical part. Okay. So those are our taps. That's how you can kind of tell when you go to pick up a tap and want to know what size it is. All that material is right there to identify it on the shank. Okay. So the last thing we're going to talk about is dies. Now, dies will cut external threads, much like you see on a bolt. Now, really the only practical purpose for a die is to clean threads up. You don't really run around taking round stock and making your own bolts. Okay, really impractical. So basically, what we use the dies for is to clean up fasteners. Okay, so if we've got a bolt, or if we've got a stud that's welded into a piece of material, we can't take it out easily, but the threads are marred. Okay, there's a couple different ways to do that. One of the easiest ways, if you've got the room around that stud or that bolt or whatever the case may be, is to use a die. Okay, I've got one over here, and it's actually the inverse of a tap. Okay, now this is the die right here, and it's got internal threads so that it will go over, using my finger as a fastener. We can now start cutting threads on here, or like I said earlier, we really just want to use this to clean them up. Okay, so, and this is a tap handle right here. Okay, not the same type of tap handle some of you are used to. Okay, at your favorite saloon. This is a tap handle that you use out on the shop floor. Okay, so anyway, it's tapered on the inside. Okay, so that it'll accommodate the fastener. Okay. Kind of eases over there, and it starts to engage the thread pitch a little bit of the fastener. Sorry about that. And it'll start working its way. It's almost like a nut. It'll start working its way down the helical spiral of the fastener. But these are hardened teeth, and these teeth will clean out the threads or clean up the threads and kind of reestablish the thread on the fastener if it's been damaged, if it's been hit by a hammer or dropped, or something's been run across the threads and they get mashed. This die will clean them up really well. Okay, it's a good idea to use a cutting oil on it too. Even though it's just cleaning them up, it's a good thing to do. So you just run this down the fastener, and it will clean those threads up for you. Okay, they come in the same sizes, and the identifier information on the die itself is right on its face, okay? I don't expect you to read this, but there's information right here. For example, this tells me it's a 14 millimeter, okay? They come in metric and standards, or fractional. It's a 14 millimeter and 1.5 threads per millimeter. There you go, I get it, okay? So they come in metric and standard sizes. So really that's about all we use taps for, okay? We can clean up pipe threads with them as well because they cut externally. These are used on pipe threading dies. There's a lab that I think you're working in with in AIT 1201, I think it is, and you have to cut some pipe, all right, or maybe 1202. But anyway, you're going to be cutting some pipe. That's got a machine that's got dies on it. They'll pull it up on this black iron pipe and cut threads, okay? But for our purposes, this is for cleaning up fasteners. You can clean up some pipe threads there as well. But that's pretty much what dies are used for, okay? So we've talked about drills, we've talked about taps, and we've talked about dies just a little bit, okay? So make sure you read the material in the textbook pertaining to these, your assignments there on Blackboard. This lab exercise you're going to be using is kind of cool. So you'll come to the lab and do some of this work with the taps and the dies and the drilling. So that's what I've got for you right now. If you have any questions, you got any concerns, or something's not making sense to you, by all means come see me. I'm in the lab mostly on Tuesdays and Wednesdays, but I'm always in the office. You can email me or call me. But other than that, that's what I got for you. Thanks for watching, and we will see you in the lab.